we're going to talk about distributive laws. Now, this is a story about the interaction between two different monads on the same category. Now, you might say to yourself, wait a minute, I thought distributive laws were all about addition and multiplication of numbers. Well, that's going to be one of our main motivating examples, but there's a much more general situation we can think about. Now, the idea is that a monad is a way of describing algebraic structure somewhere. So if you have two different monads, then you're thinking about two different algebraic structures. And you might ask yourself how you could think about combining those two kinds of algebraic structure in the same place, but in a coherent way, not just in any old way. So for example, in a ring, you can add things together, and that's one kind of algebraic structure. You can also multiply things together, and that's another kind of algebraic structure. And what a ring does is it combines the addition and the multiplication in a coherent way. And what's that coherent way? Well, they have to interact with each other properly via the usual distributive law that we all know and love. So here's how we make that into an abstract theory about monads. So if we've got, let S and T be monads on the same category, so they're monads on a category C, and you can think to yourself that this is the category of sets, for example, then a distributive law of S over T is a natural transformation I'm probably using too much board up here, never mind. Lambda, which goes from ST to TS. So what you want to think about here is that we're bringing S is distributing over T, so we're sort of bringing S over T to the other side. Now, of course, this has to satisfy the obvious axioms, and hopefully you can work out for yourself what the obvious axioms are, because, what should they be? Well, S and T are both monads, so this distributive law, this natural transformation, jolly well ought to interact properly with those monad structures, right? So, let's see, such that the following axioms hold. So first of all, let's get lambda to interact properly with the monad structure of S. So what do we have? We have an eta and we have a mu. So if we start with, let's see, if we start with T, then we can take ourselves down to ST by doing the eta for S and T on the right. But we can also take ourselves down to TS by doing T on the left and the eta for S on the right. And of course, here's our distributive law, lambda. These are actually, these are sort of double arrows really, because they're diagrams of natural transformations. So this diagram has to commute, and that says that lambda interacts properly with the unit structure for S. Now we've got to have lambda interacting properly with the multiplication structure for S. So what could we have? Supposing we had S squared, I think I need more space, S squared T, then we can move, we've got two S's here, right? So we can move them across one by one. So first of all, we get STS, and that's if we did S lambda. And the other thing we could do, then we can do the next S, so we get lambda S, and that takes us to TS squared. Very good. Now we can come down here by doing the mu for S followed by T. That takes us to ST. And we can come down here by doing T followed by the mu for S. And that takes us to TS. And then we can do our lambda across the bottom here. And that needs to commute. So that says that lambda interacts properly with the multiplication for S. Now we've got the diagrams for T as well. And I might as well draw them up because they're sort of nice. So we've got, we want to go from ST to TS, so along the bottom. But now we're going to start with an S at the top. And so here we're going to do S and then the eta for T. And here we're going to do eta for T followed by S. So that has to commute. And then over here we're going to start with an S and a T squared. So now we've only got one S, but we've got two T's over which our S has to hop. So first we hop over the first T, which takes us to TST, so that's by lambda T. And then we hop over the second T, and that takes us to T squared S, and that was by doing T lambda. Now down the sides we can do S and then the multiplication for t, or we can do the multiplication for t and then s. This one takes us to st, that one takes us to ts, and then we can do lambda along the bottom, and that has to commute. Okay, so that's the definition of a distributive law. Now you might say to yourself, well, how on earth does our ordinary distributive law for multiplication and addition fit into this very abstract looking framework? It would be a bit stupid, right, to call it a distributive law if our most basic example of a distributive law wasn't one. So let's show what's going on there. So here's an example. We're going to work in the category of sets, and then S is going to be the free commutative monoid monad. Free commutative monoid monad. That's a multiplicative monoid. And T is going to be the free abelian group. Monad. Okay, so now let's see what lambda. We're going to define a distributive law lambda. Lambda x therefore has to go from stx to tsx. So what's stx? First we're going to take elements of the free group. So we're writing this one as multiplication and this one as addition. Okay, so T of x is formal sums of elements of x. Things like x, well let's see, things like a plus b. Right? Now S of something is formal products. So now we're going to take products of sums. So we're going to get things like a plus b times c plus d, a formal product. So now what you have to do, we have to send it to an element of this. What's this? S is products, T is sum. So we have to send it to a sum of products. Oh, well we can just multiply out the bracket, right? So we get AC plus BC plus AD plus BD, which is our usual distributive law, and then we can check that it satisfies the axioms, which basically tell us that if we had more in parentheses here and we were going to remove them, then nothing terrible would happen. Now, what this tells us, well, it tells us about lots of things. It tells us about the interaction between monoids, groups, and rings. So what we get out of this, so this is what we're going to talk about next time. We're going to see we have the following things. First of all, we've constructed the free ring monad. This turns out to be the free ring monad. So TS becomes the free ring monad. And the other thing that this is telling us is that if we start with a monoid, and we look at the free group on its underlying elements, okay? So supposing X was a monoid to start with and we looked at the free group on its underlying elements, we could define a multiplication on that. Because what would we have to do to define a multiplication? We would have to say how to multiply two formal products. Well, we use this distributive law and we can then say that we're going to evaluate it like this using the multiplication in the monoid. So what this tells us actually is that the free group on a monoid is a group, and that makes sense. So what this tells us is that we can take the free group on a monoid via the distributive law. So what that's telling us is that the free, more formally it's telling us that the free group monad lifts to the category of monoids. The category of monoids. So what we'll see next time is that this is one of the key results about distributive laws that you can always do in the abstract. We're now going to look at the abstract story behind our favourite example that we've just seen. Remember, our favourite example of a distributive law is about combining monoids and groups to make rings. So what we're going to do now is the main theorem that gives that. Now it's worth, I should probably point out that one thing I didn't say last time is that here's our favourite example, right? We take our parentheses like that, we multiply them out and we get this, and we get a distributive law going in this direction only. There's definitely something directional going on here. You can't take an arbitrary sum of products and necessarily factorize it like this. So we don't have something going this way. This is definitely a non-invertible sort of situation. Now, what that means for us in practice is that we have to remember which direction everything's going in, and that means, of course, that half the time we get it wrong, and we can't remember our lefts and rights and our ups and downs, but never mind. It's just important to keep a slightly clear head about it. Right, so here's the point. The main result for distributive law theory is that a distributive law lambda of S over T, is equivalent to, now remember what we said, that we can lift the free group monad to the category of commutative monoids. And abstractly what we're doing there is we're lifting T to S alg is equivalent to a lift of T to a monad T prime on S alg. Remember that the other part of this story that we liked, the sort of subplot or parallel plot to the story, is that TS, in our example, became the free ring monad. So it gave us a way of constructing rings. And what we're going to do here is say that TS becomes a monad. Moreover, the algebras for TS were rings. And also, when we lift the free group monad to the category of commutative monoids, it turns out that the algebras for that are also rings, which is really rather exciting, frankly. And so TS alg is equivalent to T prime alg. So let's just think about this last part here. What would it mean for TS to become a monad? I mean, just forget about this abstract result for a second, and think about having a monad T and a monad S. Is TS necessarily a monad? Well, what would it have to be a monad? We'd have to, okay, when is TS a monad? We need a multiplication. We need something from TS to TS. Do we necessarily have such a thing? Well, if only we could move S over T, then everything would be okay. Because then we could move S over T, and we'd get T squared and S squared, and then we could just hit it with the usual multiplication for T and multiplication for S. So what we need here is something from ST to TS. Hurrah! If we have a distributive law, then we've got one of these things. And then the axioms for a distributive law ensure that this is a monad. This satisfies the monad axioms. Satisfies the axioms. Monad axioms. Okay, so that's all very well. What about this lifting business? Let's think about the lifting business. So let's just forget about trying to make TS into a monad for a second. Think about what on earth it means to make a monad on S alg. So if we start with an S algebra, it's got an underlying object X. This is the action, the algebra action theta. Of course, there are some axioms here. What we want to do is we want to define some action that gives us a new S algebra, which is supposed to be on the underlying object. It's supposed to be given by T. Right? So what we need is for an algebra action, we have to get an algebra action from STX to TX, because that's what an S algebra would look like. Now if we hit this algebra with T, what would we get? Well, we'd get something not quite in the right place, because it would go from TS of X to T of X via T theta. Oh, but fancy that! We've got a lambda in here, lambda X, that gives us exactly what we need, at least for this to look like it might be an S algebra, and lo and behold, as if by magic, the axioms give us that this really is an S algebra, and that really is a monad. So the distributive law axioms give us that T prime is a monad on S alg. Okay, so much for that bit. Now what about this business of the algebras for T prime being the same as the algebras for TS. So what's an algebra for T prime? Well, the underlying object here is going to be an S algebra, okay? Because T prime is a monad on S algebras. So here's an underlying S algebra for us. S, X going to X, right? And here's T prime of it, which goes from S, T, X to T, S, X via lambda X. Then we go via T theta to T of X. Right, so now we need an algebra action, so it has to be a map of S algebras going down here. So what's that? It's a map of the underlying object, so that's a phi, let's say, such that this diagram commutes. Now if you look at this a little bit carefully, what's it telling us? Well, here we've got an underlying S algebra, but actually what we've got here is also an underlying T algebra. So what this is telling us is that an algebra for T primed is something which is simultaneously an algebra for S and an algebra for T, such that they interact properly via lambda. And this makes sense, right? If you think about what a ring is something which is both a group and a monoid, but not in any old way. It's got to be such that the group structure and the monoid structure interact properly via the distributive law. And that's exactly what this is saying. So now let's look at what an algebra for TS is. An algebra for TS. Well, that's just something with an underlying object and some algebra map like that, which we better call something else. Let's call it psi. So you can sort of see how, given one of these over here, you certainly get one of those by going like that. But given one of those, how on earth do you get one of these? Well, the key is to remember that what you need is the structure of an S algebra and the structure of a T algebra. Right, so now let me just come up here a little bit. So the point is that this gives you a way of evaluating many more things than you need just to be a T algebra and an S algebra. So how can you find the T algebra action from inside here? Well, you take your action and you just locate the bits that you need out of TSX. So you only want to know, for this to be an S algebra, you only need to know where in here are the SX things. So you use eta. So this is going to be what's it going to be? It's going to be eta t evaluated at SX. And then for the other part, you only need to find the t parts. So you're going to go from TS using eta S. What's it going to be? It's going to be t of. Wait, that's not right, is it? You want to go from Tx to X, so you're going to take T of eta S evaluated X. So if you think about this in the monoids and groups case, what this is telling you is that you've thrown in lots of multiplications and additions, all kind of jumbled up on top of each other. What you want to know is where is the multiplication structure? You just want the multiplication structure. So you look for it inside the place where you've got multiplication and addition. This eta picks out the places where the T structure was trivial, so all you've really essentially got is an S structure. This one picks out the place where the S structure was trivial, so you're sort of finding only the things that count as multiplications in there. Let's see, T is the free group monoid, so you're finding only the things here, you're finding only the things that have addition, where all the multiplicative parts were trivial. And basically that gives you the outline of how you take an algebra for TS and extract from it one of these things, thereby getting that the category of those is equivalent to the category of those. Today we're going to talk about monads again, but this time we're going to talk about monads inside an arbitrary 2 category. Now usually a monad is a functor together with a couple of natural transformations, and what that means is that we've done something inside the 2 category of categories, functors and natural transformations. But of course we can try and do that inside any old other 2 category, and we get the definition of a monad inside another 2 category. So given let C be a 2 category, that's a strict 2 category, So you can secretly think of this as being like the two category cat, e.g. cat. Then a monad inside C, a monad in C is given by, this should all look very familiar, it's a 0 cell, an underlying 0 cell X, a 1 cell T from X to X, and a pair of 2 cells, eta from 1 to T, and mu from T squared to T. You know, I feel like I've said this a lot recently, but maybe it wasn't to you. Anyway, so these have to satisfy the usual monad axioms. Satisfying the usual monad axioms. Now, in fact, we don't just get monads in a 2 category, we get an entire 2 category of monads inside any 2 category. And this is what happens in Street's paper, The Formal Theory of Monads. So what we have to do now is we have to think up a notion of morphism of monads. So what's a morphism of monads? A monad functor well, we've got to take a pair of monads, so we've got, here's one monad, S, well, it's S1 on X1, and here's another monad, S2 on X2. So a monad functor from this sort of thing to that kind of thing is going to be given by, well, you can sort of guess what it should be at the first place, because certainly we've got to have some way of getting from X1 to X2 in the first place. So it's given by a 1 cell U from X1 to X2, and a 2 cell that somehow tells us about the interaction between these two things. So what it's going to be is something called, let's say, lambda from S to U to US1. So we could try drawing this as a square. So it's going to go from, so here's U, and here's U again, and here is S2, and here is S1, and our lambda has to go in here. Now you might think that this is somehow going backwards, because this is something going from the 1s to the 2s, and this 2 cell here is going from the 2s to the 1s. But the point is, the point that's really going on here is that we want, if you think about these as ordinary monads on categories, so this is a category with a monad on it, and this is a category with another monad on it. And you can then think about the algebras for this monad and the algebras for this monad. And the thing we're aiming for is to be able to get a functor from these algebras to those algebras. And it turns out that to do that, you need this thing going in this direction. Otherwise, everything's going to go backwards. Right, so now we need a notion of a transformation between these things. So if you look at this carefully, oh, I forgot about the axioms, satisfying some axioms. And, well, you see, I could be all category theorist about this and say it's satisfying the obvious axioms, but actually the axioms are sort of interesting, so I think I might even tell you what they are as a special treat, because it's nearly Christmas. Right, so what are the axioms? Well, what do you think the axioms? What do you think the axioms should be? Well, look, we've got this thing here that's got some monad structure and some other monad structure. So the axioms are going to tell us that this thing jolly well ought to interact properly with the monad structure. That is the eta for this thing and the eta for this thing. So, and the mu for this thing and the mu for that thing as well. So let's do the etas first. So here are the axioms. Well, we've got S2U going to US1, and then there are 2 ways that we could go down there from U. We could either do the eta for S2 with U on the right, or we could do the eta for S1 with U on the left, and that thing has to commute. And if I weren't so damn lazy, I could draw these as double arrows because they're really commuting diagrams of 2 cells. And the other axiom is that we've got to interact properly with all the mu's everywhere. So if we have, the point is to think about this as S2 sort of moving over the U. and turning into an S1 as it does so and sort of leaps onto the other side of the U. So if we started with a couple of S2s, we could leap them over the U one by one. So the first time, we'd leave one of them on the left, leap one of them over the U and turn it into a 1. And then we've got this other one which we can leap over, so then we've got 2 of the S1s on the right. So this here is a S2 and then a lambda. Don't know if that's legible. And this is a lambda and then an S1. The other thing we could have done was we could have started by doing mu down here, mu of the S2, and landing on an S2U. And over here we could have done U and then a mu of an S1, and landed on U S1. And then we could have just leapt the S2 over the U all at once, like that. So those are the two things that have to commute to be a monad functor. Finally, we can look at what it is to be a monad transformation. And you should be able to work out what this is as well, because what's the underlying data for this? We've got a 2-cell, no we haven't, we've got a 1-cell and a 2-cell. And so the data for a transformation should jolly well be a 2-cell between different ones of these, and some axiom telling us about the interaction with the 2-cell. So that's exactly what it is. Maybe I'll take these axioms off. Monad transformation. So let's just work out where we're going from and to. We're going to have, here's x1, s1, which is a monad. Here's x2, s2, that's a monad on x2. Here's one monad transformation, and I'm going to call this u lambda. So that's u1, lambda 1. And here's another one, which is u2, lambda 2. And we're going to look for a monad transformation between them like that. So this is given by a 2-cell between the 1-cells. So it's a 2-cell from, so let's just make sure this type checks. I mean, we've got, fundamentally we've got a U1 like this, and we've got a U2 like this. So we're going to look for a 2-cell sigma living in there, and it's got to satisfy the obvious axiom. Satisfying, well, let's hope this axiom is really obvious. So you could do sigma on here, right? Maybe I need more space. No, maybe I don't. I probably do, actually. Never mind. So you could do U1 going to U2 sigma here, and then the lambda 2 for it. So we're going to have, coming down here, we've got S2 and S1, and we've got our lambda 2, and that's got to be the same as doing it the other way around. So we've got our lambda 1, which lives in here. That's a 2. And this is an S1, that's an S2. Who's this? That's a U1. This is a U1. Here's our lambda 1. Here's our sigma. And that has to commute. So what we get is an entire 2 category of monads in C. This gives us, this gives a 2 category of monads inside C. And you can go home and check that it really is a 2 category. Today, we're going to look at distributive laws from a more formal point of view. Now, you might think that we'd already done them so formally there was nowhere else to go, but there is. Because what we can do is we can look at the 2 category of monads in C. Now, why on earth would we want to do that? Well, here's the punchline. Let's see if I can get this right. That monads in C are precisely distributive laws. Now, if your brain hasn't exploded yet, let's have a look at why that is true. So let me just draw a line down here, because what I've written on the board here is a recap of what the 2 category of monads in C is. So we're starting with an arbitrary 2 category C, which could be the 2 categories, categories, functors, and natural transformations, but it could also be something else. Now, the 2 category of monads inside C has, well, it's got the 0 cells, which are the monads, so that's a thing like this. The 1 cells are the monad functors, which are things like that, and the 2 cells are the monad transformations. So now what we're going to do is we're going to look at the monads in C. So what is a monad? A monad in monads in C. Now, just to remind ourselves, this is a 2 category, and we can take monads inside any 2 category. We just have to kind of remain calm when we do this. A monad inside this 2 category is one of these, right? It's a 0 cell equipped with an endo 1 cell together with a pair of 2 cells like this. So it's a 0 cell inside this 2 category. So it's a 0 cell in monads in C, i.e. a monad in C. Like this, equipped with an eta and a mu. Eta and mu. So now what else do we need? We need an endo 1 cell on this thing. So we need a monad functor from this monad to itself. So that's this lot of stuff. So we need a 1 cell from XS to XS. So what's that? I.e., we've got a T from X to X. Well, that's already promising, right? Because what I'm going to tell you is that we're going to get a pair of monads and a distributive law between them. And we've got a lambda from, oh look, it's from ST to TS. Well, fancy that. That's looking quite good now for being a distributive law. What else do we need? Well, we need some axioms, and we need to show that this is really a monad, right? But look, this has to have an eta and a mu with it. Okay, so we've also got 2 cells, eta and mu, and you can take it. Well, you can take it from me. Why should you trust me about this? You can go home and check that this eta and mu here actually turn T into a monad. These make T into a monad. Now, a priori, this is just a 1 cell in C, right? But to make it into a monad, we just have to give it an eta and mu. And giving this entire structure an eta and mu results in giving T, this T here itself, an eta and mu. So the final thing we need is, we need the axioms for this actually to be a distributive law. And these come from the axioms for this thing here to be a 1 cell in the first place. Because in order for this to be a monad functor, this has to satisfy, well, what does it have to satisfy? It has to interact properly with the monad structure for S and the monad structure for S. And if you look at what those axioms are for a monad functor, and you substitute in this thing, you get exactly the axioms for a distributive law. So that's nice. And you may be wiping your brow now and saying, phew, we've done that. But there's actually something more to be said about this. So let's see. So I should probably just say, wipe this off. So a monad in monads in C is a 0 cell X, a pair of monads S and T on X, and the distributive law of SOT. Now, the punchline, or what I think is the punchline, is that we have something that takes C to monads in C. Right? This is a 2 category, and this is a 2 category. And in fact, this is a functor from the category of 2 categories to the category of 2 categories. The category of 2 categories. This is the category of strict 2 categories and strict 2 functors. Yeah. And in fact, we can call this monad blank because it takes C and it takes it to monads in C. And Stree showed that this is in fact a monad. It's the monad. Monad is a monad. Now there are some people who think that I only like this because I like saying monad. They're obviously wrong. So monad is a monad. What does it mean to be a monad? Well, you have to have a multiplication and a unit. And the really cool thing about this is, what is the multiplication here? The multiplication, that is the mu. So we need something from monads in C, and this has to go to monads in C. So what's this? This is an X, an S, a T, and a distributive law of ST. So an object in here is a distributive law, basically. And what this multiplication does, well, remember that having a distributive law like this gives us a monad structure on TS over here. And it turns out that the multiplication for the monad takes this distributive law and gives us back the monad TS inside the on X, which is the same zero cell that we started with. So, well, that's about all I have to say about that.